State and prove the Fermat's theorem. Statement: if p is a prime number and greatest common divisor of a of p is 1, then a raised to power p minus 1 is congruent to 1 modulo p. Now proof: since greatest common divisor of a and p is equal to 1, therefore the number of a, 2a, 3a, so on p minus a are divided by p. The remainders are 1, 2, 3, so on p minus 1, though not necessarily in the order on this order. Let r1, r2, and so on rp minus 1 be the remainders obtained on dividing a, 2a, so on p minus a respectively by p. Then the remainders r1, r2, and so on rp minus 1 are precisely 1, 2, so on p minus 1 placed in the sum order, so that the product of r1, r2, so on rp is equal to product of 1, 2, so on p minus 1. This is equation 1. Now a is congruent to r1 modulo p, and 2a is congruent to r2 modulo p, so on p minus a congruent to rp minus 1 modulo p. Multiplying these congruence relations, we get a is equal to 2a, 3a, so on p minus a congruent to r1 into r2, so on rp minus 1 modulo p. Or 1, 2, 3, so on p minus 1 a raised to power p minus 1 congruent to 1, 2, 3, so on p minus 1 modulo p by equation 1. Or p minus 1 factorial is equal into a raised to power p minus 1 congruent to p minus 1 factorial modulo p. Since p is prime, therefore greatest common divisor of p and 1 is equal to 1, greatest common divisor of p and 2 is 1, and so on. Greatest common divisor of p and p minus 1 is equal to 1, and hence greatest common divisor p and p minus 1 factorial is equal to 1. Therefore, cancelling p minus 1 factorial from both the sides of 2, we get a is congruent, a raised to power p minus 1 congruent to 1 modulo p.